Hello. Good morning and welcome to the first session of the Service Mesh track for today. I'm Risha Mars, Linkerd maintainer and track host for this session, and I'm here to introduce our next speakers. They are Anil Attuluri and, oh no, I forgot your name. My notes, Jason Webb. And they are software engineers at Intuit, and they're going to talk about Intuit's path to the service mesh and also about Admiral, an open source project that they maintain. Please welcome them.
Hello. Test. Hello? All right. Yeah, thank you for coming to our talk, Stitching Service Mesh Across Hundreds of Discrete Networks. We work for Intuit. So Intuit has three main product lines, TurboTax, Mint, and QuickBooks. We support about 5,000 developers and 50 million customers. So why were we interested in service mesh at Intuit? So in the beginning, we started out in our monolithic era, right, where we had applications that supported our big business units that didn't quite have enough velocity, and they needed to be broken up. They were too thick. So we started to move into our microservices era, where we started to decompose all of these services. So as we went through that decomposition, the cost of authoring any one service was still too high, right? So setting up the hosting, the monitoring, operating the service. So we never quite were able to break everything down as much as we wanted to. So a couple years ago, we really started to lean into Kubernetes. And as we progressed on our Kubernetes journey and our MSaaS platform, where we stitched together a lot of automation, we're able to create a lot more services and be able to sorry, I lost my train of thought there. And so we were able to actually create a lot more services and get a lot more velocity. But the biggest problem was, as we started to really look at how these services connect with each other, we really needed to evaluate the infrastructure that we were providing and how we could utilize stuff in industry to make that connection better. So that's where we really started to look at service mesh and Istio and how we could bring that service mesh into our enterprise. So just kind of a quick sample of what a service mesh might look like. So in this particular deployment, we have some toy services, a book order or book info service, and a product info service, and then a payment service. So the book info service is going to talk to these other two services. So we have a single cluster here, and we have an Istio control plane installed in this cluster. And then in between the different services communicating through a proxy, we can establish mutual TLS. So in this picture, too, we left an API gateway as the ingress point. As browser traffic comes into the cluster, it would probably use a different authentication protocol, maybe OAuth or some JWT authentication. So we still have a controlled ingress point. But this gives us the ability to get observability and intelligent routing inside of our clusters, which is great. But our enterprise is a little bit more complicated than kind of this simple diagram, right? So some of the complexities that we ran into as we looked to bring the service mesh into our ecosystem was that we actually ran a lot of Kubernetes clusters. And we ran those clusters for different reasons, right? We wanted isolation in between our different business units. We wanted our business units to be able to have autonomy between them if they had different seasonality, and sometimes they wanted to take have more caution in different parts of the year. We wanted them to not impact each other. And there's also compliance reasons, right? So if we're hosting services that are underneath maybe a PCI audit, we want to limit the scope of those audits. We don't want to have everything involved in an audit. And then also, just for environments, right? So there's different pre-prod environments, maybe a dev environment, a perf environment. And then also, as we look at hosting services across multiple regions, those services will be hosted in independent clusters within maybe the east or west region of the cloud. But not only do we have a lot of clusters, but also all of these clusters don't have L3, L4 connectivity between the pods, right? So they're actually they're kind of island networks in between each other. So as we want to have any services communicate with each other, we have to be able to ingress and egress out of these clusters. And just to kind of put some statistics on what this actually looks like, so we run about 160 clusters and roughly almost 5,400 namespaces. So the unique thing about these namespaces is that they're actually globally unique. So every namespace that gets provisioned is unique across all of the clusters. And that becomes important in sort of how we decide to stitch together the mesh in the future here. So if we take our toy problem that we started with and actually try to overlay it into something that's a little bit more realistic of a topology, we'll end up with a topology that looks a little bit more like this, where we have 3 clusters hosting these different services. We've isolated our API gateway into one cluster. That gateway happens to be a multi-tenant system, so it supports a lot of the business units, so we don't want it coupled with any set of deployments for any of the other clusters. In this particular use case, the product info service and the book order service are actually maintained by the same business unit, so that went into one independent cluster with itself. And this payment service, because it's going to be part of an audit, we broke it out and stuck it into a separate cluster. So as we look to sort of overlay a mesh onto this more distributed cluster topology, what do we actually need out of the mesh to be able to make this happen? So the first thing we need to be able to support is we need some sort of identity of what a service means. And we need this to be able to support HADR deployments, right? So because we have globally unique namespaces across all of these clusters, I need to be able to know that the same binary is being deployed in 2 regions, even though they're in unique namespaces. So we need some mechanism to do that. We also don't want to lose strong point-to-point authentication that the mesh gives you with mutual TLS. We want to keep that functionality. And we also want to keep end-to-end encryption, so we don't want to have any man-in-the-middles across the ecosystem. We want strong TLS encryption between all the nodes and between all the east-west service-to-service communication. We also want to eliminate single points of failure. So we've created this ecosystem of all of these clusters for different isolation purposes and autonomy. We don't want to then introduce another layer on top of that causes us to bring that all back together and break that level of isolation and points of failure. And then this particular one, so by default, the DNS name that Kubernetes is going to give you has the namespace and the cluster suffix put into it. That sort of starts to couple the service discovery of how you locate the service with what we would consider the administration boundary of the service, right? So if that service changes ownership or moves in between different namespaces, we wouldn't want all of the clients to have to update how they address that service. So we want those 2 things to be decoupled from each other. And then also we want to keep the developer's experience intact, right? So we don't want to have routing configuration separate from the service's actual hosting configuration. We want that to be one package that can be plumbed into their CI/CD pipelines, and it's easy to troubleshoot, and it's easy for them to be able to see what they're actually operating on. So looking at these requirements, we started to look at what's available in Istio to be able to map these requirements on to Istio. So Istio has a lot of different multi-cluster functionality in it. There's a lot of good stuff there to be able to connect things. So the first one we looked at was using a shared control plane. So in this particular use case, or this particular topology, we can see with these red lines, all the proxies will connect up into one shared control plane between all the clusters. So we can still have mutual TLS in between the services going across the clusters. And we can do that by sharing an intermediary CA that trusts the same root CA that's deployed in Citadel in those clusters. That's the open source way to do it. Internally, we have an internal CA that we use that we've extracted away from all the mesh deployments. And we can ingress and egress through the networks pretty well. But this setup didn't quite meet all of our requirements. So we didn't do anything here to sort of be able to identify a workload that's being deployed in separate namespaces. Actually, with some of the mesh network functionality, we actually force that. We want the way it's deployed, it actually wants you to keep those things the same. But we got the point-to-point authentication and end-to-end encryption with this deployment. The single point of failure is kind of a warning sign. So technically, you can make that shared control plane high availability and have multiple deployments of it. But it's something you're going to have to put a lot of care and time into making sure that doesn't break. Because if any of the clusters can't connect into that control plane to get configuration for their proxies, then you won't be able to auto-scale effectively in the cluster. And then also, we didn't do anything to necessarily decouple the naming scheme from the namespace. And now the way we author our Istio configuration is in a control plane that's separate from the service's control plane, which makes things a little bit awkward for developers. But there's another option. So in this particular option is having multiple control planes. So this would be just deploying a Istio control plane along with every Kubernetes cluster that we have. So in this particular case, all of the proxies that are running within each one of these clusters can go and get their configuration from their local Istio control plane. And we can still get all of the same mutual TLS going in between the clusters themselves. But you end up with a little bit of a problem here is how do you manage the configuration between all of these different clusters, right? Because now we've partitioned the service discovery. So how can the book order service know that the payment service is actually deployed in another cluster? And how does it get routing to get over to that cluster? There's configuration in Istio to be able to do that and author that setup, but there's no way to have it be automatic, and someone has to manually go in and edit that. So someone has to go and find, say, the load balancer of the payments cluster and put it into a service entry that's being deployed in the same cluster as the one that the book order is in. But as we look across the points that we wanted out of this, we got a couple more boxes out of it. But we didn't really solve this problem of having this single identity of a service that can span namespaces that are globally unique. And we didn't really decouple the namespace from the service discovery. But we did eliminate a single point of failure now that we have a control plane with every cluster. From a global services ecosystem, there's no one system now, it's all distributed, which prevents that single point of failure. And now any developer would author configuration local to their cluster, so it would seem very natural with the rest of their Kubernetes deployment. And also in our evaluation of this, a lot of the just the features with Istio work better within one cluster. As things go between separate clusters, there's certain features that might work better or not as well. So it's kind of a more stable deployment of the control plane. So so we had this deployment of multi-cluster, but we had this problem of how to manage that configuration across all of these clusters. So that's where we came up with this project Admiral. So the multi-cluster deployments that we do use Admiral to do this higher level configuration management. And so really what Admiral's doing is it's going in and syncing the configuration in all of these different clusters to enable the services to be able to communicate with each other. And what Admiral will do is based off of labels that can be added into the different deployments, it can be able to create a globally unique name that services can use, and then it can be able to set up the routing to those deployments that decouples the namespace topology from the service configuration. And then the other thing we created to be able to do is to be able to have multiple names for the same service. So, and to be able to create those names easy. So a lot of times you would want maybe a end-to-end environment that could be pinned within different regional routing. So I want an end-to-end environment to be pinned to an east region or a west region because maybe I want to run regression suites in different regions of that deployment as I'm migrating my deployment across my fleet. So the way Admiral actually plugs into this multi-cluster deployment is it actually sits basically on top of these deployments as a controller of control planes is the way we define it. And so what it's doing is watching these different clusters and then looking at as things come up and come down, it can then provision Istio configuration as a way to be able to facilitate these different clusters. And I guess one more point on here, and Admiral itself doesn't actually hold any runtime state. It's just syncing basically Istio state. So all of the state that's used to run these clusters is actually pushed down into every individual cluster itself. And so that means that if Admiral goes away, you're left with the current running state of all of the meshes that are across the fleet. So it doesn't impact any of the runtime deployment. So if we look at the kind of things that we wanted to accomplish, with the multiple control planes and Admiral syncing configuration, we're able to solve all the problems that we wanted to be able to roll this out across the enterprise. So Anil's going to do a demo of Admiral for a HA, or a demo with Admiral of a HADR deployment.
Thanks, Jason. OK, so today we would like to demo the global traffic routing capability that's powered by Admiral. So first, we'll look into the same toy problem that Jason was talking about. So here, if you see on the right-hand side, there's a payments microservice that has been deployed in both US West and US East regions, and that is for the disaster recovery issue. And then you have a book order service that's deployed in another cluster that actually calls the payment service for the payment processing. And then if you see, each of these clusters have Istio in them. And Istio already supports something called locality load balancing, which makes the locality-based routing possible. Basically, you route the traffic to the nearest region first, and then if that fails, you route the traffic to the next available region or next closest region. So given this, and Admiral is obviously watching all these clusters, it can watch the Istio configurations and also the services that are getting deployed to these clusters. And then it can create these global traffic policies or use them basically to route the traffic or to control the traffic in individual clusters. OK, so let's go back to the command line. So what I want to show is, so there's custom CRD, the custom resource definition that Admiral understands, which is a global traffic policy. We will look at what that looks like. Cool. So if you look at this, so it has a DNS name in it. So this is the DNS name that Admiral would create for payments, and that would be available across all the clusters. So let's say tomorrow, it's not just the order service. It might be some other service in a different cluster that's going to use payments. This name is going to remain the same. And then the microservice owner of the owner of the payment service can actually control this configuration from their own cluster so that they can control how the clients actually route traffic to their service. So if you look at here, you see the DNS name, of course, and then you see the region. So what we are saying here is at any time, if someone calls default.payments.global, you would route 80% of traffic to US West 2, and then 20% of traffic to US East 2. So, and then if you see the other interesting thing here is, so there's a selector. So you apply this global traffic policy to the names or the deployments that have this label, which is the identity label. So the identity is the unique identifier for that microservice in your entire company. So given that, what I would like to do is go back to the slide that I was showing. So if you look at this, so there's a browser or a desktop on the left-hand side. So that's calling a book order service. And book order service is in turn calling the payment service. So now we have built some UI where the payment service, first of all, the payment service returns the locality information based on which payments instance is serving that request. So if the payments request was served from West, you would get a locality header back that would say US West, and the same applies to US East. So that will help us plot a diagram on the front end. That's what I'm going to show right now. I think. So what you're looking at here is, so once we start the request, we are going to see the distribution of traffic that is being served from the payment service from US West and US East. And based on this proportion, like how many requests are getting served from East and West, these images are going to shrink or grow in size. So let me start the request. So right now we have the distribution of 80-20. So if you see, it will stabilize in a little while. So you can see that 80% of traffic roughly is going to US West, and 20% is going to US East. Now what we are going to try is go edit this global traffic policy record and flip it. So let's do 20 and 80. And then I'm going to save this and then go back. Now you should see that this reverses, and then you see that the traffic being served from US East 2 for the payments has, like, the image has grown in size. So let's stop this. So now I would like to explain, like, what's actually going on. So now what's happening here is, so whenever we update the global traffic policy CR custom resource, Admiral is watching it. And what it's doing is it's actually picking all the clusters where this payment service is being consumed from. And then it's going to go ahead and update something called a destination rule, which is a Istio custom resource, to make sure that whatever you have specified in your global traffic policy is applied to in that cluster, for the Istio configuration in that cluster. So that would make the book order service proxy get the necessary configuration for it to basically load balance or distribute the traffic. So let's get into the actual edited or like the modified. So I have created aliases. Pardon me. I want to save like seconds, like whenever. I don't want to type like kubectl every time. So if you look at the destination rule, so we looked at the global traffic policy. So this is the destination rule, the Istio destination rule in the cluster where order service is running. So if you see, the host is the default.payments.global, which the order service is calling. And then you see this locality load balancer setting. So that is basically being translated from the global traffic policy that we just saw, which Admiral understands, into the destination rule that Istio understands, or the proxy gets configuration from. And that's the destination rule. The other thing is the service entry. So default.payments.global is the service name that has been created. It's not the Kubernetes service name, which is bound to the namespace. This is namespace agnostic, which Jason was talking about. So we need the namespace agnostic names, because tomorrow, if the service moves away from that namespace, we still want to have, like, we don't want the clients to change the service name that they're calling. So let's look, and the cool part about Admiral is it does the contextual configuration. So let's say tomorrow the payment service, for whatever reason, moves into the same cluster as where order service is running. Then you don't want, like, that communication is local within the cluster. So Admiral is responsible for delivering the contextual configuration depending on where these services and their dependencies are running. So that said, let me show the service entry. So service entry is like bringing your own. So Istio Istio monitors the Kubernetes API server updates, and it watches all the services that are being deployed in a Kubernetes cluster. Now, if you want to bring in like your custom services into Istio, service entry is the configuration that you would do. Since default.payments.global is a service name that Admiral generated, it's going to use something called a service entry, which is the Istio custom resource, to do that. So if you look at this, so this is the host name. So whenever someone accesses this host name, what's actually happening is you have defined a couple of endpoints, right? So this is all automated, by the way. So this is all being generated by Admiral. You see the address. So this address is basically the load balancers of the clusters where payment services are running. So this is a cross-cluster communication that's happening. And then if you see, like there is also a locality information that is being specified for each of these endpoints. So this is also done by Admiral because Admiral knows where these clusters are deployed based on the nodes. So Admiral is going to attach these locality labels, and that's what is making this locality load balancing possible across the clusters. Cool. Okay, so Admiral is open source. So we thought, like, based on our learnings from the multi-cluster service mesh journey, we open source this product so that like the Istio community can benefit from it, and not just the Istio community, the service mesh community in general. So we would love the feedback and any like the contributions to the project. So I'm going to like go to the Admiral project. So Admiral project, by the way, is open sourced under Istio ecosystem. So Istio ecosystem consists of some projects that aid. Those are the tools for the Istio service mesh. So if you, we have like a cool example for like a single cluster setup. You guys should definitely try that. And then we also have like all the architecture and how Admiral works, and then like also defining whatever I just talked about, which is the global traffic policy stuff. Let me. Okay, so if you guys have any questions, and if you guys have any questions related to Admiral or Intuit, please stop by our booth, S47, and we are hiring. So, thank you.
Thank you.
Okay, hold on.
I may have missed it, but how do the admirals find each other? So how do they know that if you add a new cluster, how do you specify that for the Admiral instances?
Cool. So the question is, how does the Admiral know if there is a new cluster? So Kubernetes API server works off secret. So what we do is whenever there's a new cluster created, the cluster provisioning piece of it basically creates that secret that is required to talk to that Kubernetes API server, and it drops it in a central namespace where Admiral is running. So that's how Admiral knows that there is a new cluster, and from that point on, it's going to watch the cluster, and it's going to do whatever it's doing.
Yeah. One of the reasons you mentioned in the beginning why you have multiple clusters in your organization is one of the reasons was compliance. So let's say if the payment system is sitting in compliant area and some other random service is sitting in some other non-compliant area, and the CA that you mentioned is compromised in non-compliant area, how will it impact the service sitting in the compliant area? Because it seems like if they're under all sub-CA, some same root CA, then the non-compliant area compromise could impact the compliant area.
Yes, from the isolation of the trust domains within it. Yeah, so that's a really good question. So in general, we've used the same credential bases across those spaces for a fairly long time. But within the intermediary CAs, as long as they trust the same root CA, you could rotate the CA that was issuing the credentials into the compliance side.
Does the traffic from the book order to payments, does it go through the ingress gateway of the next cluster?
So there's an ingress gateway, an Istio ingress gateway that's acting as a layer 4 load balancer that's routing off of, it's doing the SNI based routing which is the kind of the connected, it's the gateway connected example, I think, in the Istio documentation sort of uses that technique. And we use the same technique. We just automate the configuration for that technique.
Just a two-part question. First one is regarding the Admiral that you mentioned, where if the service is in the same cluster, it knows that it will send the request to the same cluster. I saw the CRD, you mentioning the location where the service should route, like 80/20, whatever. So how does Admiral know when it is in the same cluster?
So it knows it because it's also watching the Kubernetes API server. So when it gets, it's watching the deployments and the services, just like the Istio, control plane. So when it's generating the entries for, like, let's say the payment service, it's going to know that, like, so it has the configuration or like the state of like what services and deployments are running in that cluster. So it's going to know that order service and payment service are in the same cluster. So it's
will
going
it
to generate
override your specification of 80/20 or?
It will not. So so in our case within the company, like, we use some annotations to help Admiral like basically define that global identifier that Jason was talking about. But you can map in any labels that you want, and then Admiral would use those labels to identify your services. You don't have to modify your service.
Just one another question, not the same, is about you mentioned about service entry need to be created in your use case, wherein the names needed to be different than the namespace generated by Kubernetes, right? Does service entry that you showed example is manually need to be created, or because I saw that the load balancer name, AWS load balancer name that you had to provide was obviously lengthy and stuff.
Right.
Does it?
Yeah. So the way that is done today is exactly. Yeah, you have to set that up manually. If you were to, like, there isn't a tool today that will do that. So Admiral will do that. It will discover the load balancers and it will automatically update those entries.
Yeah, hi. Thank you for a good presentation. What was the main use case for using Istio inside a particular cluster? You spoke about multi-cluster Istio setup here, but within the same cluster, what was the key use case for using Istio there?
So Istio is implementation of service mesh, right? Like Jason said, like we were like in the microservices journey, and service mesh would bring in a lot of capabilities. And Istio is one such implementation. So we picked Istio based on our evaluation internally within the company as to like which service mesh technology we should use. And then given that, based off that, we developed Admiral, which would automate that configuration. Probably Jason can add.
Yeah, I think some of the routing capabilities were pretty useful. The telemetry collection, being able to get the point-to-point mutual TLS with certificate rotation. I think that's something that we've have a lot of application teams implementing security protocols. So being able to externalize some of those security protocols so we can enforce credential rotation is a pretty useful feature. So those are some of the things that made it pretty attractive to us.
Is Admiral just a layer on top of Istio, or is Istio like the way you guys deploy it? Is it highly customized?
Our Istio deployment?
Right, or is it Admiral doing all the customization?
Yeah, Admiral is really tailoring Istio to our needs, I would say. We do have a fork of Istio internally, but it's pretty close to the actual mainline. Other than, like we said, we don't use Citadel necessarily. We use an internal CA. So there's some modifications that we do to the installation to set up some of the trust across the control plane to use an internal CA. But that's the main change that we keep with it.
Does Admiral work with Citadel?
It does. The demo we just did uses Citadel for it. So.
How often do you keep Admiral updated to the latest releases of Istio?
The one you're running off of is off of Istio's master right now.
Yeah. So just to give some context on that, so the Istio had capability to like do this locality-based load balancing, the destination rules that I showed, where something like that we submitted a PR to Istio because Istio didn't support service name level locality load balancing. It used to support only the cluster-wide, meaning like all services would use that 80-20 distribution or none of them, right? And then to support, like to get this capability in Admiral, we had to first go do some work in Istio itself to override that and support like a per DNS name locality-based load balancing. So whatever demo we just showed, that feature is getting released in 1.5 Istio and the latest Admiral, of course.
So does Admiral run on EKS or like another Kubernetes cluster, right? A separate Kubernetes cluster, right?
So it also runs in a Kubernetes cluster, yeah.
Okay. But how is your setup like?
We use we have internal Kubernetes cluster management. We haven't we are moving to EKS, but not yet.
Okay. And does it support, like if I have cluster between EKS, OpenShift, does Admiral still support it? Is there any challenge you guys can see?
So it really depends on, so one key thing here is the load balancer names that we have shown. So those are like the cloud native, not the cloud, the provider native names that get created. So as long as you have the support for the Istio Ingress gateway to get a public facing DNS name, I think you should be good, yeah.
And the node like the Admiral is running, like it needs to access to all the clusters, right? So in this case, like the IAM role or the instance profile should be like much more higher, like, access to this. So do you have anywhere like documented, like, what are the types of policies you'll be using in that Admiral cluster?
Yeah. So, yeah, go ahead.
Yeah, you can, I mean, in that example, there's role definitions for the access that Admiral needs. In general, the Admiral only has, it reads different information from the cluster, but it only writes some of the Istio configuration. So it has write access basically to Istio configuration, but reads some of the Kubernetes types and Istio configuration. But it's the rules are fairly well locked down, as tight as we can make them at least.
It seems that you sort of build like a service discovery, like you build some sort of global service discovery, right? What was the reason to not use a service registry for that, other than just like Kubernetes CRDs to register? Because you map a CRD to a few LO balances, right? That will then use SNI to route. And as a segue, how would this work if the call was not coming from, for example, the books, but coming directly to the payments through a GLB, right? Will the weights still be applied and things like that, or it's because from the perspective of the app owner, right? I want, like, my perspective as an application owner for payments, I want the knowledge of the balance. It doesn't matter, like, necessarily who's calling me,
Yeah. So this particular implementation implements that name and that locality routing is all native within the mesh itself, right? So it doesn't have any, it's not outside of any of there's no visibility outside of it. So if you addressed that payment service from a point that was outside of the mesh, that would need an external DNS name, certificates that match it, and so on and so forth, right? So internal to the mesh, we're able to manage that and then allow Envoy to give us that layer 7 control over the global routing pieces of it. So.
Yeah, and the external traffic would be coming through the API gateway, which would be participating in the mesh as well. So that would solve that problem, basically.
Thank you. Great presentation.
Okay, thank you. Thank you.